What if I told you we could build some of the most advanced materials on Earth, not by cutting them down to size, but by building them up, literally one molecule at a time? Well, today, we're diving into a powerful process that does exactly that. Okay, just take a look at this. It's a material called an aerogel, and it's one of the lightest solids ever created. It's so incredibly porous, it's something like 99% air, which gives it this wild, almost ghost-like look and makes it an amazing insulator. But here's the real kicker. This intricate, high-tech solid doesn't start out as a solid at all. It actually begins its life as a totally unassuming chemical solution, just a simple liquid in a beaker. So the big question is, how in the world do you turn a liquid into something that looks like it's from the future? Well, that incredible transformation is all thanks to a method called the Sol-Gel process. All right, so here's the key idea you gotta wrap your head around. Instead of taking a big block of something and carving it away, the Sol-Gel process is what we call a bottom-up approach. You're literally building the material from scratch, starting with individual molecules just floating around in a liquid. Okay, so how does this whole thing actually work? The best way to think about it is kind of like a high-tech recipe. It's almost like a form of kitchen chemistry. And just like any good recipe, this one has 4 basic stages. You start by mixing your ingredients, then you form a special kind of liquid, that turns into a jelly-like solid, and finally, you dry it all out to get the finished material. First up, you mix together your main ingredients. They're called precursors, but you can just think of them as your tiny molecular building blocks. You mix them with a solvent, a little water, and a catalyst to get things going. Right now, it's just a plain old clear liquid. And this is where the magic starts. Through a reaction called hydrolysis, those precursors react with the water and start forming these tiny, nanometer-sized solid particles. They're so small they just hang out suspended in the liquid. This mixture is called a sol. Then, a second reaction called condensation kicks in, and all those little particles, they start linking up, holding hands, and branching out until they form one giant continuous 3D network all throughout the liquid. At this point, the liquid is trapped inside this new solid skeleton, and we have what's called a gel. Seriously, just think of Jell-O setting in the fridge. It's the same idea. So now we've got our gel, but it's wet. It's full of liquid, and getting that liquid out, that's the next step, and it is a huge fork in the road. How you choose to dry it will totally change the kind of material you end up with. So if you just let the liquid evaporate normally, surface tension acts like a giant fist, and it just crushes that delicate network as the liquid leaves. That gives you a dense, collapsed material called a zero gel. But if you use a really clever technique called supercritical drawing, you can sneak the liquid out without creating any of that crushing force. You preserve the original network perfectly, and what you're left with is an incredibly light aerogel, literally an air gel. And you can really see that fork in the road right here. See, on the left, the aerogel keeps that open, airy structure. But on the right, the zero gel has collapsed in on itself, becoming way more dense. It's a fantastic illustration of how one single choice in the process can lead to 2 completely different materials. But here's the real superpower of the Sol-Gel method. It's not just about making gels. It's about the unbelievable amount of control it gives you over the final material's properties. By carefully tweaking things like the pH of the solution, the temperature, or even just how long you let it react, scientists can basically become master chefs. They can precisely tune the recipe to dial in the exact density, porosity, and structure they want, all on a nanoscale level. And here is a perfect example of that control. This graph is basically a fingerprint of the material's internal structure. Notice how at a low pH, the line is just flat and boring. That means the structure is a total mess. Completely random. But watch what happens as they just nudge the pH up. Bam! These sharp peaks shoot up. That's the signature of a highly organized, perfectly crystalline structure forming all from one tiny little tweak. And here's what that actually looks like under a microscope. At that low pH, you just get a clumpy mess. But as you dial up the pH, you start to form these beautiful, distinct, uniform nanoparticles. This level of control is exactly what makes the process so powerful for designing custom materials. Okay, so this level of control is really cool, but what do we actually do with it? Well, this is way more than just a lab curiosity. The Sol-Gel process is actually the secret ingredient behind a huge range of real-world technologies. The crazy thing is, from that one single starting sol, the process can shoot off in all sorts of directions. You can spin the gel to create super strong ceramic fibers, you can precipitate it to make really uniform powders, or you can just paint it onto a surface to create an ultra-thin film. It's just incredibly versatile. And that versatility makes it absolutely perfect for creating advanced coatings. What you're looking at here is a ridiculously thin film of titanium dioxide on a piece of glass, all made with the Sol-Gel method. This kind of coating is used in things like solar cells, high-tech sensors, and even self-cleaning windows. And the applications are literally all around us. That anti-glare coating on your glasses, good chance it's Sol-Gel. The bioactive glass used in medical implants that helps bone regenerate, yep, Sol-Gel. It's also driving huge innovation in energy storage, electronics, and even in cancer therapy research. Now, this all sounds pretty amazing, and it is. But this method isn't a perfect silver bullet for every single situation. Like any technology, it's got its own set of trade-offs. The huge upsides are that you can create materials that are incredibly pure and uniform right down to the molecular level. It's also a low-temperature process, which saves a ton of energy. And of course, you get that unbelievable control over the final product that we've been talking about. But on the flip side, it can be slow. Like, really slow. Sometimes taking days or even weeks. The high-purity chemicals you need to start with can also be pretty expensive. And there's always the risk that the whole thing could shrink or crack during that drying phase if you're not super careful.